afternoon, Professor Mihai Damian from University of Strasbourg. He speaks on the topology of monotone Lagrangian submanifolds.
So, thank you very much to the organizers. I'm very glad to be here in IMPA in Rio again. So, I will talk about my favorite subject, which is the topology of Lagrangian submanifolds. So, the general question is the following. Let's have a symplectic manifold and then Lagrangian closed submanifold embedded in M. And then the question is, which are the constraints on the topology of L induced by this fact? So I will only talk today about two ambient symplectic manifolds, which are M equal to Cn, M equal to Cpn. So first, for M equal to Cn, which is called the local case for obvious reasons. So what are the, first, the obstruction, the known obstructions to the existence of such an embedding? First of all, we have that the Euler characteristic of L is 0 if L orientable. And if L is not orientable, this is a multiple of 4. This is a very, it's a result of Audin in the 80s. Of course, this obstruction has no effect if L is of odd dimension. So I will mainly talk about odd dimensional manifolds here. And then we, of course, have this famous theorem of Gromov saying that pi1 of L cannot be trivial. Now, the examples we know. So, first of all, if n equal to 1, it's obvious. If n equal to 2, the only examples are the torus in the orientable case. And then this is and in the non-orientable case, we have to have the Euler characteristic is 4k, and this is the construction of given time. Except that for k equal to 0, there is this the result of Nemirovsky showing that the Klein bottle has no Lagrangian embedding. And for general n, so historically we have this result again of Audin saying that if L is immersed in Cn minus 1 immersion, the immersions are flexible, they obey to the H principle, right? So then L times S1 embeds into Cn. On the basis of the known examples in the 80s, there was a question of Audin. Again, the question is, if L in Cn is orientable, is L a product with some S1, or at least does L fiber over the circle? And the answer turned out to be negative. So a few years later, there were some results of Polterovich. So Polterovich showed that if L in Cn is immersed orientable with k double points, let me consider here that n is odd. Actually, there is a statement for n even too, but as I said, I will mainly talk about n odd in this case. Then L connected sum with k, with k copies of S1 times S2P embeds as a Lagrangian submanifold in Cl. And this produced some examples like, say, T, the torus, connected sum with the torus, connected sum with S1 times S2P, and then again connected sum S1 times S2P 3 times. Those are Lagrangian submanifolds in C, 2P plus 1. And then very recently, actually, there is a result of Eliasberg, Ekholm, Emmy Murphy, and Ivan Smith, that actually we can consider here in the statement of Polter-Orbich, we may consider if n odd, we may take k less than equal to 2. And actually, if in the particular case of the dimension 3, we can take k equal to 1, and then the result is quite interesting. If you take any L3 orientable, there is some Lagrangian embedding of L connected sum with S1 times S2 into C3. So actually, one could say that in this case, the situation is quite flexible. Except for this condition of Gromov, we have a good amount of flexibility. Now, if we impose the monotone condition, so if L is monotone, meaning that there is a proportionality between the Maslov morphism and the integration morphism, positive proportional. So if L is monotone, the situation is very rigid. More precisely, so I proved the following, and actually independently it was proved by Evans and Kedra. That is, if L is of 3 dimension is orientable in C3 Lagrangian monotone, then actually L is a product with S1. So this should be compared with the statement of Fukaya, which says that if L is orientable Lagrangian and prime into C3, then L is S1 times sigma G. But as far as I know, there is no complete proof available for the moment for this statement. actually. So and now for for greater dimension, let me give you a statement for greater dimension. Again, in the monotone case, so if Ln in Cn is monotone, no, sorry, that's not that. So if n is odd and L is a connected sum of k manifolds, each of them satisfying the following condition: the odd dimensional homology of their universal cover is 0, which is the case in the examples we have here, then there isn't any monotone Lagrangian embedding of L into Cn. So these are the statements for Cn. Now, for Cpn, now of course in Cpn we have all the Lagrangians coming from Cn, and we have also Rpn as examples. There are others. And as abstraction, we have this new theorem of Biran and Cornea, saying that if L is Lagrangian in Cpn, and if 2 times H1 of Lz is 0, then the homology of L is the one of the real projective space. And I slightly improved that by proving actually that in fact L has the homotopy type of Rpn in this case. Is there a question?
The question is if in theorem 2, which homology group is 0 implies that there are no monotone Lagrangian embeddings?
So the odd dimensional homology groups of the universal covers of any factor here. All of them. Like in these factors here, right? So actually, morally, the examples of Polterovich cannot be embedded as monotone ones. This is the. It's automatically monotone because of this. Okay. So it would be, of course, interesting to have results for pi ones which are for say for morally infinite pi ones. And then there is another statement of Fukaya saying the following. So if L is in Cpn, and this time L is aspherical and spin, then there is a relative homotopy class of Maslov number 2 such that when we take the boundary in pi 1 of L, the centralizer of G, which is the set of gamma such that gamma commutes with G. So this set is of finite index. So again, no complete proof of this is yet available. And there is a result in the monotone case. So proved by Schatz, who's a student of mine, showing that this is true if L is monotone orientable. K pi 1. And there is also another result, in some sense analog to this, but much weaker, saying that if you have k copies, connected sum of k copies of S1 times S2p for p greater than 1 and k greater than 1, 2, of course, then there is no monotone embedding of this into CPM. So, probably there are more abstraction to come about this, about these manifolds. Now, let me stop here with the statements and tell you some words about the method which can be used to prove all this. So the method is called lifted floor homology. And it's a combination of floor homology with the properties of the universal cover. Before I describe it, let me do some Morse theory for 5 minutes. So Morse theory, you take L and you take a Morse function, and then you take a gradient, a generic gradient, and then so you define Ck of f, which is spanned by the critical points of index k. And then you define the differential by counting the gradient lines between points of consecutive indices. So you have the x is some index of y equal to index of x minus 1, and you count these gradient lines from x to y. And so you have d square of x, and when you have d square of x, is actually, you count the broken orbits from x to z times z, and this, so index of z. So this is 0 because these broken orbits arise by pairs. So actually you have these Morse figures from x to z. Of course, everything is modulo 2 in this talk. So because of this, you have delta square equal to 0. Now, if you want to, so of course, this yields a complex, and whose homology is isomorphic to the homology of L. Now, if you want to do the same thing on the universal cover, it's natural. It's a natural construction. So you take the universal cover, and you consider the complex, which is infinite dimensional, spanned by the fibers of critical points. And then you lift the gradient lines from x to y, and you define as before a differential like this on this complex. And the square of this differential is still 0 because all these Morse figures lift on the universal covers. So again, the broken orbits arise by pairs. Right? And so you get a complex here whose homology is actually the homology of the universal cover. This one way to see this is that actually the stable manifolds of X span a CW complex whose differential is exactly the Morse differential, and what you get when you lift is just the lifted CW structure on the universal cover. So therefore, it computes the homology of the universal cover. So yeah, one more remark here. Of course, if you fix one point in each fiber of the critical points, then you can see your complex as, so this complex becomes free, a free complex over the group ring spanned by so this is the point of view I will take for the Floer homology afterwards. Now, let me now go to the Floer setting. So I want to do the same for Floer homology. And in order to have Floer homology well defined, let me take L a monotone Lagrangian in some symplectic manifold. And then L1 is the deformation of L induced by some Hamiltonian diffeomorphism. So you define the Floer complex as usual. So this is spanned by the intersection between L and L1, which are supposed to be transverse. And afterwards, so this is a complex as a module. So to define the differential, you count holomorphic strips for some compatible J between two intersection points X and Y. And so you write dx is equal to the sum of, for the dimension of the moduli space equal to 1, the sum of this this kind of holomorphic strips. Of course, you have to translate by R in order to, as you do in the Morse setting actually, times Y. So if you want to do the same for the universal cover, what you do, so you take again the universal cover, and then what you obviously have to do is to take as a module the infinite dimensional complex spanned by the fiber of the fibers of the intersections, and you define the differential as being dx tilde is the sum of the path is from x tilde to y tilde times y, where the projection sends this path on the universal cover on a path here on L from x to y, which is the part on L of a holomorphic strip. So actually what you do is you take holomorphic strips, and then you take the path. The path is they define on L, and then you lift these paths on the universal cover, and with this data you define a differential. It's somehow in an analog way of what we did in the case of the Morse, setting. Now let's see if delta square is equal to 0. And this is you have a very simple example, or should I say, probably, as we'll see, it's a counterexample, which is a circle in C2, and which we move with the translation. So you have here 3 holomorphic strips, each of one defining some path on this circle, which is called L. So this defines this path A, this one defines this path C, and this one defines this path, which is called B. And when you write dx, first downstairs, you find that it's this path times y plus this path times y, and then dy is this path times x. So that when you write d square of x, what you'd find is this concatenated path times x plus bc. So C goes this way, B goes this way, times x. So there are 2 of them. Of course, modulo 2, this is 0. But when you lift it to the universal cover, here you have a circle, here you have a contractible path. So when you lift all that to universal cover, d square of L is not 0. So why is that so? This is the case because this kind of Morse figures I was talking about, so the existence of these Morse figures is given by the compactness in the space xz, the space of dimension 2 of xz. So this is a, say, Morse compactness in the Morse case. But in the Floor case, this compactness fails precisely if x is equal to z and for the mass of number equal to 2. It fails because you can, in this case, you can have a bubbling disk. And it's the only situation when you can have this kind of obstruction. More precisely, if you can have a holomorphic strip going from x to x. So this is the part of the boundary on L1. This is the part of the boundary on L. And this holomorphic strip converges. Either this loop shrinks to a point, and this gives a holomorphic disk of Maslov 2 passing through X with boundary on L. Either this loop shrinks to a point, and in this case, what we get is a holomorphic disk of Maslov. So of Maslov 2 sitting on L1. And this is exactly what happens in our example here, because this concatenation of two paths actually we can. So before saying that, I would say that in this case, instead of having normal Morse figures like the one in the picture, we can have Morse figures with one broken orbit on one side and one disk with boundary on L or on L1 on the other side. And this is what happens in our examples here, because on one side we have this concatenated broken orbit A and B, and this one is connected with this holomorphic disk. And the concatenated orbit B and C is connected with the other holomorphic disk sitting on the other Lagrangian, as shown in my picture. So now, if d square is not 0, the question is then what is it? How can we express this d square? So writing as before, d square x. Now downstairs, for instance, d square x is the sum. So I will take the broken orbits. Now the broken orbits arise in pairs except for the case where x is equal to z. So in this case we have compactness, so we have normal Morse figures. And as I said, in this case it could be one broken orbit like that could be connected with a holomorphic disk. So actually, so of course one has to prove something here. So it's a result by O that in fact this is the same as counting the holomorphic disks with sit on L or on L1 times X. Okay. So of course these are These are infinite number. This is just the number of those is just the pre-image of the evaluation defined on the disk with mark point, one mark point on the boundary. Okay. Now, this square. So actually, this square, when we look at it downstairs, it's still 0 because there is a result saying that if L is monotone, Maslov number 2. So when we count the disk passing through an X, a generic X, with boundary, so forgot a Hamiltonian isotopy. So when we count the disk of Maslov 2 sitting on L, and then we count the disk of Maslov 2 sitting on L1, we get 0 modulo 2. This is the case in our example, since we have the two of them. So when on L, d square is equal to 0, which enables one to define Floer homology, usual Floer homology for NL equal to 2. Now, if we look at the universal cover, then of course it's different because these disks here count in a different manner. And which is the manner we should count then? So this one, if it's on the boundary of L, remember that what we take is the path which is drawn on L. So if you want to count a disk with the boundary on L, this should count with this G is the homotopy class in pi1 of the boundary, right? On the other hand, if we count a disk with boundary on L1, this will count like 1. This count like 1 because in this case, this part on L will shrink to a point. Okay? So actually at the opposite side of the Morse figure, it will give a contractible loop. Okay? So all in all, what we find is that d square of x on the universal cover. So of course we have to fix some point in each fiber in order to have this complex as a complex of a ring group, as I remarked before in the Morse case. So on the universal cover, it gives this formula. So now I will write 1 plus G because modulo 2, this disk, as O states here, these disks are in the same number modulo 2. So I have the same number of G's as a number of 1's modulo 2. So I will take 1 plus G. And then here I will write this. So this is the number modulo 2 of disks. I call this MJX, which are disks sitting on L of Maslov 2 and passing through X and defining the homotopy class G. Okay. So this is the formula. Now we tended to define a lifted floor homology. Now it's not always defined, but the one nice thing about this lifted floor homology is that you have something if it's defined, and you have other results if it's not defined. So in both cases, we have some properties. Now let me give you these properties. First, of course, this is defined for NL greater or equal to 3, because in this case, this compactness obstruction doesn't exist. It only existed for a disk of Maslov 2. Now, if it is defined, then you have, as in the usual case of the floor homology, Lagrangian floor homology, you have this spectral sequence which starts from the usual homology, but this will be the homology of the universal cover, and which converges to the floor homology, to this lifted floor homology. More precisely, so if you take as L1 a graph of a differential in some Weinstein neighborhood of L, then the Floer complex is exactly as a module, the Morse complex of F, of course. And then if you choose well, if J is well chosen, then actually the Floer homology can be decomposed by the Morse homology of F for some gradient plus, and this dI go from Ck of F to Ck minus 1 plus I times NL. And then when you write that the Floer differential square is 0, what you get is that delta 1 goes from the homology of the universal cover to the homology of the universal cover according to the shift given there, and then delta 1 square is 0, and afterwards delta 2 goes from the homology of the homology to the homology of the homology, and then again on this delta 2 square is 0. So you get this H infinite of L accordingly, and this is 0 only as in the usual setting of the spectral sequence, if and only if this lifted Floer homology is 0. And this shows that in some cases this Floer homology cannot be defined. So this shows that is not defined so first, for first for displaceable k pi 1s. Because in this case, so when we take di from h0 to hi, this is 0. Okay, so then the lifted floor homology, if it was defined, it would be non-zero, but on the other hand, since it's displaceable, it should be 0. So this is a contradiction, but it can be defined. More generally, for orientable L displaceable, this is -1 plus I times NL here. It's the shift. Displaceable, orientable, displaceable, such that H, so this comes, this condition, which I put on my hypothesis. And this is because of the same reason. If it's orientable, this is even. So this, again, is 0. So again, this spectral sequence, it's valid. It cannot converge to 0 because this element here survives in the spectral sequence. Okay? So, and as a consequence, for three-dimensional L orientable with infinite pi 1. So in all three cases, this floor lifted floor homology is not defined, and this actually implies with one NL less than 2 for all these three situations, and this is what is called the Auden conjecture. Okay. Now, let me turn to the case where it is not defined. There are two facts. First of all, so this came from a discussion I had with Jean-François Barrault. Now, suppose it is not defined, and then take if it's not defined, then there is, I don't know if I still have the formula on the blackboard, then there is at least one G here with the number of disks inside, which is odd. So let such that this number of disks with boundary in G is 1 modulo 2. Then take an arbitrary, still generic path in pi 1 Lx. Now this path can be used to define a cobordism. And the cobordism, so let's take the homology class of J in H1 of L. And then you have this, so take this disk with one mark point of the boundary and mu equal to 2 GL, so sitting on L. And so if you send this as usual in L times L with evaluation and gamma, then if you take phi minus 1 of the diagonal, what you get is a cobordism. So the cobordism between so here I put the homology class of G. Now let me depict that. So this is 0, 1, and this is M. So here you have this element of M, Gx, and you have the cobordism between them and the other side. Now, what you can have is you take this element, which this time is on M, G homotopy X, okay? And you can have this kind of figure in the cobordism. But then, if this W1 is of NGX, what you see on L is this kind of figure. So you have a disk here starting, and then at some point it goes back here. And what you obtain here is that actually this point here is also belongs also to the same, this boundary belongs to the same homotopy class, G. Okay? And afterwards, remember that here in this MGX you have an odd number of elements. So there is at least one which has to travel on the other side. One here in MGX. Okay? But when it travels on the other side, what you see, so this, what you see in L, so what you see is that you have this gamma, and you start with this disk, and when you go along gamma, and you end up here. Now here, you are no more in the same homotopy class. You are in the class of M gamma J gamma minus 1x, which in particular implies that this class has at least one element. Okay? But on the other hand, there are only a finite number of disks in all. So this all implies that in this case, so if the Floer homology of L is not defined, then this set is finite, a set of conjugate elements with G is finite, which actually means that the centralizer of G in pi 1 of L is of finite index. Okay. And another consequence I won't talk about here because I don't have many time, even if it's easy. If you note this element here by lambda as an element of the group ring, so another consequence is that B, if it's not defined, then this lambda cancels the universal homology of the universal count. So this gives at least another situation where the Floer homology, lifted Floer homology is defined. So this Floer homology is defined if pi 1 of L is a free product of infinite groups. And in particular, if L is a connected sum, because in this case, this property cannot be true, because you cannot have this subgroup of finite index. So in this case, the floor homology, the lifted floor homology is defined. Now, let me go to at least a proof of one statement. I gave. So take L, as I said, a connected sum in Cn, which is monotone, Lagrangian, orientable, and such that H, so the odd dimensional cohomology of the universal cover is 0. Then we have that FH of L is not defined because sorry. So one can prove easily that this odd dimensional. One can prove easily that in this case we still have this property. So this floor homology, lifted floor homology, is not defined. But on the other hand, what I showed here, that this is 2, 3, shows that actually FHL is defined. So this is a contradiction, which shows that actually this kind of manifold cannot have a monotone embedding in Cn. So yeah, I don't have much time to say more, but with this game between defined and not defined, we can have some obstructional topology of monotone manifolds, and hopefully there are other cases to be done next. Thank you.